Swayam Prabha. Digital India. Educated India.
Welcome. We are going through the lectures of the class High Performance Computing for Scientists and Engineers, and this is the second module, which is Introduction to the module is OpenMP Programming, and we are continuing with the lecture 13, which is continuation of the previous lecture, lecture 12, Introduction to OpenMP. We will continue it for one more lecture also. The subsequent lecture will also discuss about Introduction to OpenMP. So, in the previous lecture, we have discussed about threaded parallelism. I gave some introduction to shared memory systems. We have looked into shared memory systems in much detail earlier when discussing about parallel computing architecture, but I also try to give another view on introduction of shared memory, introductory shared memory system. This view is a programmer's view on that given a problem, he has to identify what are the parallel regimes, he has to launch the threads, and there are sequential regime of any program. None of the program can be fully parallelized. There will be some sequential part of the program. In the sequential part, only one thread will be active. When one goes to the parallel part, he can launch number of threads. What will be the number of threads? That can be determined by the programmer, that can be also determined by the person who is executing it. There are some thumb rule for finding out number of threads for different cases. Some of these cases we will discuss, but he will launch a number of threads. So there is a single thread which is active in the sequential part, then multiple threads are launched when the parallel part of the program is coming, and then again when this parallel part is over, it will join the threads and one of the threads will be only active. And we looked from a programmer's point of view. In a sense, we looked at how these threads can interact, how these threads can write data to memory systems, some features like this. So we'll go more directly onto OpenMP in this lecture, and we'll have some introduction to OpenMP. After that, what OpenMP is, who developed OpenMP, these things we'll discuss. After that, we'll see, which is very important, how we can compile an OpenMP program and execute an OpenMP program, and can we do it in our own computer? What are the software we require to launch OpenMP? We'll look into OpenMP programming model and followed by data handling part in OpenMP. So these two will be completed in this lecture and the subsequent lecture. OpenMP is an application programming interface or API which supports multi-platform shared memory multiprocessing programming. It can be used in different platforms of shared memory multiprocessing programming using C, C++ and Fortran, and this is very important. OpenMP cannot be used directly. You cannot just write an OpenMP program. You have to write a C, C++ or Fortran program on which you can use OpenMP as function calls, as library function calls, and it's an API. So this is C++ Fortran and this can be used on various shared memory platforms with different instruction set architectures and different operating systems like Solaris, which comes from Sun, AIX, HP, Linux, Mac OS, Windows. On different type of systems and with different operating systems, you can learn OpenMP jobs. But these OpenMP programs are basically C, C++ or Fortran programs. So you have to first write a program using say C, and in which you can include OpenMP library calls, and then you can get multiprocessor program using a shared memory system. That will be the OpenMP parallel program. OpenMP consists a set of compiler directive, library routines and environment variables. OpenMP provides a portable and scalable platform for programmers to develop parallel programs. Portable means you can port it from one platform to another. You can develop it somewhere else, you can run it in another platform. You develop a program in your Windows platform, you take it to a server, a Linux server and run it there. It's scalable. You can develop a program and test it up to say 20 processors. You go to a 64 processor system, you can still run this program. So it can be scaled to larger number of processors. So one important point is that it consists the compiler directives, library routine and environment variables. So when you write, when you use OpenMP, you have to use some of the directives inside your program, some of the library routines which will be called. So some directives will go to the compiler, some library it will run, and it also have to set some environment variables. Programmer can add OpenMP constructs over sequential codes to convert to a multi-threaded parallel program. This is extremely important thing for scientific computing experts. If you have your own program to solve say gravity wave equations or finite element method for sunbeam bending, etc., you identify that this part can be parallelized, you can write OpenMP construct over your sequential code, over your C code. You can write some OpenMP lines and convert it into a multi-threaded parallel program. So parallelization of already existing sequential program is quite well doable using OpenMP, and that is one of the goal of OpenMP. We will see how OpenMP was developed and how it's standardized, and we can understand that this has been one of the driving force of getting OpenMP available to different people across different fields, so that they can convert their sequential code to multi-threaded parallel program. Or if you are developing your parallel program from scratch, you can write it something like a simple C code, adding some of the OpenMP constructs. OpenMP is managed by the non-profit technology consortium OpenMP Architecture Review Board, jointly defined by major computer hardware and software vendors. So if we, as I said, if we go back to history when parallel programming came, and especially threaded programming came, some of the thread parallelism languages were very low level language, that you have to be an expert in computer programming, or you have to be very well conversant in computer science field in order to develop the parallel program. And however, it has been seen that the major users of parallelism are not people who are experts in specifically computer programming, but people who are coming from background of science, engineering, finance, etc. So then at certain point of time, a consortium is formed between hardware and software vendors, because they are the people who has to sell it to a wider community so that they can use parallel architectures as well as software for using parallel programs. So they came and formed this OpenMP review board, and this board sits down very frequently and finalizes different releases in OpenMP. So whatever OpenMP we see today has been developed over last few decades, last couple of decades, and has been finalized by OpenMP Architecture Review Board. And if somebody develops something, that is given to all the hardware and software vendors who are member of this review board. So it's a non-profit organization who manages it. But why is it given that? To keep OpenMP portable. If you develop it in a Windows platform, it should run in Solaris also. So whatever developments coming from a group who are working with Windows, this development must go to all the other software vendors. If you are developing something in HP, it must also run with Dell. So this is managed by OpenMP, and this is specifically for the purpose is that in some sense users from other community will come and learn OpenMP programming. And this has been, I said, standardized over last 20 years in SMP or symmetric multiprocessor programming, and also for non-uniform memory access multi-computer programming. OpenMP has been standardized, and very recently, say in last couple of years, OpenMP has also developed for GPU computing. So using OpenMP, you can you can launch multiple threads in GPU and get utilization of GPUs. So we'll see it briefly when we'll discuss about GPUs, that how OpenMP can be used for GPUs. But right now we may mostly focus on the symmetric multiprocessor or uniform memory access UMA type of SMP, and see how OpenMP can be used for that. And this is simply there is a common shared address space in which multiple CPUs are connected, and each CPU can access the data elements in that address space and update it, and the CPUs are working in parallel. They are executing concurrent stream to update different locations of the memory element. This is the programming model which will follow in this part of this discussions. So, and now if we come to the software subsystems of OpenMP, that how OpenMP works in terms of the software development and software based operation of a parallel program, OpenMP based program, how does it work? So we can see that there is of course some hardware. There is a shared address space memory, DRAM, which is connected with multiple processors, and over this hardware OpenMP will work. So if we go from a bottom up approach, so in this what will be required, that some executable will come, and this executable will be running through all the processors connected with the main address space. So you need an operating system which will support for shared memory access of different processors, and what we called as multi-threadings, that different threads are active over different processors connected to the same shared memory system, has to be supported by the operating system. And when it is supported by the operating system, we will send the instructions to the operating system, and that will be done by OpenMP runtime library. This is the systems layer, this is the software systems layer, which is operational over the hardware layer. Now comes the programmer layer. If you write your OpenMP program, what will you do so that your OpenMP runtime libraries are called and they are interacting with the operating system, that the jobs are launched in different processors concurrently connected with the same address space. And for that, programmers will write the directives inside the program. When it will compile, this will call the OpenMP libraries. Programmer has to call the OpenMP library functions, and the compile job will link to the OpenMP libraries and ask the OpenMP runtime libraries to interact with the operating system to execute the program. And also the programmer can set some of the environment variables, say on how many processors it should run or how many threads will be active at one point of time, which thread will be specifically asked to do something else. So these sorts of environments, OpenMP, the programmer can programmer can specify inside the code. So this is programmer's layer, and above that once this program is ready, and he compiles and gets an executable, this can be used by the end user, who is basically from an application area, who has a program, say on computing some of the economic cost benefit matrix, and that is parallelized by the programmer, which is going through the systems and finally launched in the hardware, and the end user is only running the OpenMP program for the application he wants to solve. So this is typical hierarchy of OpenMP software subsystems, that user only knows that he has an application job which has to be worked. A programmer has taken the application, wrote a program. Inside he has included the directives and which will call the library functions during compilation, and he will also set the environment variables, and this will go to the when in the systems layer of the OpenMP library, runtime libraries will be active and will interact with the OS, and the OS will launch the jobs, operating systems will launch the jobs as multi-threaded jobs connected with the shared memory system. This is taken from Tim Madsen OpenMP hands-on tutorial. If you go to OpenMP annual review board site website, the official website for OpenMP, which is openmp.org, you will find a very good collection of materials, including textbooks, including lecture notes and tutorials on OpenMP. You can self-learn OpenMP using those, and there you will find Tim Madsen from IBM Corporation has prepared a hands-on tutorial for OpenMP. You can find that this is very useful tutorial for learning OpenMP. And as I said, it's like learning a language, if not a language, but it's like learning a paradigm of programming, and only through the video lectures you cannot learn this. You have to get your hands dirty. You have to pick up some of the problems. I'll show, best thing what I can show you is how to write the parallel programs, but you have to pick up some of the problems, and if you are actually interested in learning parallel programming, you have to start writing your own parallel program on that problem. And while doing that, you will of course face some of those difficulties which I bet I cannot clear through the video lectures. So you have to go to an exercise of self-learning, and some of the resources like Tim Madsen's tutorial and some more which I'll mention later in this lecture will be very important there. Okay. So what becomes the next important step is to how to install OpenMP. If you have to self-learn OpenMP, if you have to run OpenMP programs, you need a platform where you can compile the OpenMP jobs. So important part is installation. Fortunately, if you have IGNOU compiler or GCC compilers for C, G4tran, Fortran, you already have OpenMP in case this IGNOU version is greater than 4.2.0. So starting from version 4.2.0, IGNOU has started including OpenMP in the GCC release. So if you install GCC, automatically OpenMP is installed there. You can compile OpenMP programs. So GCC version of 4.2.0 or higher must have OpenMP features configured in it, but it has to be only with C, C++, Fortran. These are the three languages for which OpenMP support is given. And why is these three languages? Because the users who will require OpenMP for which is mostly for some of the domains in which multi-threaded parallelization will find importance, they are mostly conversant with these three languages, and most of the programs for scientific computing, for engineering applications, and also many for economics or finance calculations are developed in C, C++ and Fortran. Keeping that in mind, OpenMP.org, so the OpenMP annual review board or the vendors who came and formed the consortium for OpenMP made OpenMP supportable for only these three languages. And if you have IGNOU, as said, OpenMP is already there. If you want to use it with some other compiler like Intel compiler or PGI compiler, you can go to openmp.org and see how to install it for the other compilers. OpenMP is free, so if you have a commercial compiler like PGI, on top of that you can install OpenMP. Availability of OpenMP doesn't require paying from your site. It's a free software, and it can be used with any other compiler, as I said. So for compilation, you have your OpenMP program, you use GCC, you have to write GCC, the program name, and -f OpenMP is the compiler option. So if you write GCC a.c -f OpenMP, you will get an executable which is a thread parallelized OpenMP executable. And if you run this executable simply, it will run on the number of available cores in the SMP. In the SMP or symmetric multiprocessor, or the computer in which you are using, which has multiple processors connected with a same common address space, the number of processors will be the number of threads if you just compile a program, OpenMP program with FOpenMP and run the executable. If you want to launch some different number of threads, and this is what is an environment variable, that how many threads will be active, you have to set OMP num threads externally or inside the program. In that case, you can run it in different number of threads. If you use Intel compiler, the compiler option is minus of OpenMP, and it will again, if you do not set the environment variable, by default it will go to the number of cores of the SMP. If you are using Portland Group's compiler, PGCEC or PGF90, etc., then the compiler option is minus MP, and it will be by default launched in one thread. So, it will be essentially a sequential program. If you have to launch it into multiple threads, the program is same. If you execute it, if you simply run the executable, it will run as a sequential program, because it will go to launch only one thread. If you have to launch it in multiple threads, you have to again use this environment variable. I will show you in a while, and set the numbers. It is important to set the numbers of threads before execution of OpenMP codes, or also you can change the number of threads while executing the OpenMP code. So, compilation and execution on which you have, it is important to set the number of threads. So, if you are using a Linux terminal, the command export OMP num threads is equal to 8 will set the number of threads. Now, you run your executable, it will go to 8 processors. So, build your executable using the compiler command gcc program name and the compiler option minus f OpenMP. You will build an executable. If you simply run the executable in a quad core machine, it will run in 4 processors. But if you set OMP number num threads is equal to 8, it will launch 8 threads. Earlier it was run on 4 processors. It was, if you run on a quad core machine, it will by default run 4 threads. If you set this number, the number of threads will be set to 8. In practice, the number of threads is not greater than the number of cores. Why? Then there will be load balancing, there will be threads distributed in different processors, different threads will be distributed in different processors, some will get less, some will get more, then that things can happen. So, in practice we see how many cores are available, and number of threads is not greater than number of cores. In rather better practice is to set the number of threads less than the number of cores, because some of the cores will be always active on some other job. So, just for running OS, some core is active, for some of the graphics interface, some core is active, etc. So, if you have a 8 core system, if you run the job in 6 core, then these 6 cores are probably free if you are not running anything else in any other job. The other 2 cores are doing into something else, graphics or OS, etc., internets. These 6 cores are free, and you can best utilize this 6 core. If you run in all 8 cores, some core is already doing some other work, so it will be slower. There will be some job division, some runtime division in between your OpenMP program and some external program in that core. So, one core will be slower, other 7 cores are faster, therefore, there will be some latency in that. So, best is to run in number of cores which is little less than the total number of cores available in the CPU. Though the number is set before the execution, like by the environment variable export num threads is equal to 8, or if you do not set it, it is set to the default of the compiler. Number of cores available for Intel and GCC, and now 1, the thread number is set 1 for PGI. So, though it is set before the execution, either by export num threads or either by this or whatever is set by the compiler, but it is also possible to run some instances at less number of threads, and that can be done by writing that this is an OpenMP directive. After the directive, you specify num threads is equal to 4, then this job will go and run in 4 threads. I will show you an example. that you can change, therefore you can change the number of threads while executing the OpenMP job. Runtime functions though may also set as different number of threads, like you can do while executing, you can set somewhere OMP set num threads is equal to 4, you can write this runtime function, and that means the next parallel part will be executed in 4 processors unless you change the number somewhere. And execution running the OpenMP compiled executable directly will launch the parallel program. For executing the OpenMP parallel program, you have to do nothing, just run the executable. And before that, we believe you have set the number of threads if it's not specified within the program. So programmer can specify it within the program, or the person who is applying it, who is the application person who is running the program, can set the number of threads by export num variable. So if it should be already set, or it is the default, and then if you just run the executable, it will launch, the parallel program will be launched, and wherever is the threaded part in the parallel program, wherever you have given some constructs like parallel, and these threads will be launched, they will be launched in the variable that has already been set or in the default number of variables. So we will see it as an example. So and we come to our first OpenMP program, which is a hello world program. Let us see what happens here. It's a C program, starts with include omp.h. This is the header file required in any C OpenMP program. This specifies that there is a OpenMP program and links all the OpenMP libraries, and inside which the then stdio stdlib.h, which is standard header files, int main argument c character argv int, and then we write the pragma omp parallel. This is a OpenMP directive. It shows that the next regime must be OMP parallel regime and run in multiple threads. There will be multiple threads launched here. So we write int id omp get num threads printf hello world from thread id with the so int id is the number of the thread number, and it will write hello world from this number of thread. And this is a simple program. You can write this C program, just copy it and run it in your computer if you have GCC. So how to run it? Sorry, we'll see how to run it. This is the OpenMP header file. This is the directive for parallel region. So whatever is within the brace will be run as threads, as multiple threads. And what will be the number of threads? The number of threads is what is set by the set num thread variable, by the environment variable. And here the parallel, here the parallel region will end. Here to here is the parallel region, and after this the parallel region ends, and if we write anything, that will be a sequential operation. Only one thread will be active here, multiple threads will not do. So after this parallel, the next brace will be the parallel part of the program. Multiple threads will be launched here. And this is a runtime library functions. We are calling about runtime libraries. This will during operation for each thread, it will return what is the ID of this thread, and this is through the OpenMP runtime library functions. This will return the thread ID. So if we execute it, export OMP num threads is equal to 8. We set the number of threads is 8, and then write a dot out. It will write hello world from thread ID, and from different threads from 0 to 7. There are 8 threads. So from 0 to 7, it will write each thread will write hello world. So though only one hello world from thread ID is written, only one hello world printf hello world is written here, only one printf option is given here, there will be multiple threads. Each will execute their own printf option. If we change the number of threads, here it is 8, so 0 to 7, the first thread is thread ID 0, the last thread is thread ID 7. Thread IDs always starts from 0. So if you run on 5 plus threads, the thread ID will be 0 to 5 minus 1, 4. So it will run from 0, 1, 2, 3, 4. And we can see that the output of these threads are not in ascending order, because it is not a do loop, it is a parallel loop. Different processors are writing this. So, different processors may have different latency to the IO system in the screen, and they can write it on their own. It cannot be synchronized very easily, very straightforward. There are some ways to synchronize it, but if you actually use your parallel environment, utilize your parallel environment, they will be written in some unknown order, in some random order, because different processors are trying to write it. It is not synchronized as of now. So, we continue it in the hello world program. As I said, outputs are not written sequentially. It is not one by one. They in some random order, the threads have written their output, and each thread is been executed in different processor if we use multiprocessor system. Can this code be run as threads less than the set number of threads? We have noticed that before running the threads, we have executed the OpenMP library environment call set num threads is OMP set num threads is equal to 8 or 5. Can we run it in different number of threads? And we can see a simple example. If nothing specified, number of threads is the default or set by export before execution of the program. Else the number of threads can be specified by runtime function OMP set num threads or by a clause. So, either by this function or by a clause parallel construct directive. So, when we wrote that this section is parallel, OMP parallel this, here we can also write the number of threads in a bracket, and then this can be changed. So, programmer can change the number of threads. We will see the example that here we wrote OMP parallel num threads 4. That means this parallel regime will be launched only in 4 threads, and then later we wrote OMP parallel int-id OMP get num threads, fine, but there no clause is given after parallel. So, what is the default number of threads? It will run on that number of threads. So, if we run this program, this part will run in 4 threads because the number of threads is set as 4. This parallel part is first it will write hello world and then it will write again hello world and the thread ID. This parallel part is not given any clause, so it will run on the default number of threads. And we can see that export num threads is equal to 8, a dot out, and this hello world is from 0 to 3. 4 threads will be active here. After that it will launch another parallel regime and again hello world, and this because we have set it as default and the default number of thread is 8, which is set by OMP num threads. This will go to 0 to 7, this will go in 8 parts. Well, interestingly we can see that one parallel part ends here, which is in 4 processors because we have given the clause num threads 4. The other parallel part starts and ends here. Therefore, there is one set of parallel part. If we put anything here, that will not be a parallel part, that will be executed as a sequential part, and there will be another set of parallel part. Or one parallel loop ends, another parallel loop starts. We can so launch different groups of different parallel loops one by one in a OpenMP program. Different regions of the program we can parallelize, and sequentially there will be a sequential following of the parallel regime. But one part of parallel program will be there, then something will go on sequentially, then it will be followed up by another group of parallel threads, and the number of threads we can change at different instance. If we take a Fortran program, so in Fortran the program hello world is written. Interestingly, in Fortran we do not have to include any header file. A parallel loop in Fortran, the braces are not there, so parallel loop will start with OMP parallel and it will end as OMP end parallel, and these are not exactly Fortran commands, so this is started with exclamations which are comments in Fortran. So, if you do not use the OpenMP compiler option, then this will be treated as comments, it will not be a parallel part, it will be executed as sequential program. If you add it, then it will be parallelized. and in Fortran any integer starts, by default integers are given I, j, k, l, m, n, any variable starts with these letters are by default integer, but OMP get num threads returns as integer value, so it has to be externally specified as integer. It's not a by default integer. That is what is Fortran semantics. So by default it's real, so you have to externally specify it as integer. So if we run it, set export num threads is equal to 8, and when we ran it we saw that hello world, so it should run on 8 threads, therefore we'll get hello world from thread, and this is thread id which is obtained by OMP get thread num, that will give the number of the thread, specific thread. So this will be 0 to 7. However, we see 7 and rest all are 2. So what we are seeing in C, it was coming 0 to 7, but here in Fortran it didn't come 0 to 7. So there must be something wrong in the program. And this is very interesting. We will look into it in the next lecture also. That variable, the ID, variable ID, which is writing ID, it's a shared memory system. So this ID is being shared, written in the common global address space. So when each thread is trying to write ID, it's writing the ID, variable ID, which resides in the shared memory. Therefore, the value ID must be same for all the threads. So what happened, for when the the last thread was active, it got its own value ID. Then the third thread, which is thread number 2, is active, and it wrote the value ID to the shared memory location. The other threads, while writing the value of the ID, that got the value ID which is obtained by the thread number 2, the third thread. Because this is a shared memory variable, but it should have their own thread ID. So this thread ID is also being shared, and each one is writing the same thread ID. So variable ID must be different for different threads. However, different threads must be different for different threads. However, it's being a shared memory systems, if one thread writes something and other threads might pick up the same value which is written by other threads, not its own value. So the solution will be declaring it as a private to each thread. Instead of being a shared variable, ID should be extra defined on top of the regular definition of the variables. ID should be apart from that defined separately as a shared variable, as a private variable, that it's not shared. Each thread has its own copy of the variable ID. In C, anything used within the parallel loop, not used outside the parallel loop, is by default a private variable. In Fortran it's not, but it's a good practice to see which variables are private, because when the threads operate they execute the same line for each. So you cannot write for thread ID 1 it's ID 1, thread ID 2 it's ID 2, so on. It's the same variable ID which all the threads will write, but in a shared memory system they will essentially end up in writing same value, if not for one, but in general they will essentially end up in writing same value for all the processors. So you have to define parallel private ID. ID will become a private variable to all the processors, and the processors will write hello world from ID, and this ID is parallel, so each processor or each thread has its own value of ID. And then you will get the variables 0 to 7. So those C, because ID is not called outside the parallel loop, in C it will behave as a private variable, but in Fortran it is not so. But it is also a very good practice to identify the private variables. They are few in number. What are the private variables? The variables whose value will be different for different threads, and specify as the clause to the parallel regime that these variables are the private variables. We'll look into these important some more important aspects of OpenMP program in next class. Thanks.